So we're going to start looking at the source-free RC RL circuits. And this time around, first part, we are going to focus on the source-free RC circuit, the resistor capacitor circuits. All in all, in this type of circuits, we want to see what happens when a circuit, or maybe for some reason in our circuit, the source which was maybe present at some point is removed. The circuit remains without the source, and the only source or the only thing activating our circuit is going to be a capacitor. So that becomes a resistor capacitor circuit without any other power source. And usually those circuits, you'd have a case where maybe here you have the capacitor itself, and then here you have a resistor. Here we're looking at the simplest type of circuit, and then afterwards look at examples where you have some more complex systems, but the logic will still be the same. Here you have a resistor R, here you have a capacitor C, and then you have a current that goes to pass through the capacitor. Let's take this current as IC. And then you have the current that comes to pass through the resistor. Let's take that current as IR. And then at some points here, you have the two nodes. Maybe this is where the power source was initially connected. So since this is where the power source was initially connected, and these two, the capacitor and the resistor, they are connected in parallel. It implies that the voltage they will be fed will be the same, since they're basically in parallel. Of course, they'll only be in parallel if you have a source connected at some point. But without the source in play, when you only have this, meaning when it reduces to a resistor capacitor circuit just like this, of course, this is basically just a series connection. Okay, so what is happening here? So in this case, if you just isolate one point, even if you just get, let's say, the node, just picking off the nodes here, let me say this is node A, let's say this is node B, just pick any one of these nodes here. When you pick node A, you find that RC is leaving the node, IC leaving, so minus. IR, not RC, IC is leaving, negative. IR is also leaving, so negative IC. IR, I mean. Since you only have the two, this must be equals to 0. Or you can look at this as IC plus IR is equals to 0. In the end, when you look at the expression for current through a capacitor, again, these are the expressions we were looking at earlier. We came up with the equations. For a capacitor, the current through it, what did we come up with? After differentiating, we ended up with the current through a capacitor as equation 1. It was the capacitance multiplying dV dt. So we have here, this is going to be capacitance, then dV dt. Then for a resistor here, we're going to have plus. So for a resistor, it's very straightforward. Ohm's law, V is equals to IR. So the current through a resistor will just be the voltage divided by its resistance. So this will just be V over R is equals to 0. From here, what do we see? We can try to play with this expression, divide everything by C, we end up with dV dt plus V over CR is equals to 0. And then finally, I'm trying to isolate, I want everything with V on one side, now take dt the other side. Multiply everything by dt. You have dV is equals to V, and not equals to. I can take the other expression to the right side. So I'll say, let me keep it like this for now. V dt over CR is equals to 0. I'll take this to the right side, becomes negative. Then I'll bring the V to the left side, so that I have dV over V is equals to -1 over CR. Do you have a question?
You are writing, but I can't see. What I can see is just the headline.
All I'm doing here, bringing the V this side, I've brought the V to the left this time around, and the dt is this side. Here I am just trying to solve this equation for V, and the technique I'm using here is separation of variables. I think it's a technique that you get to look at in math later on under differential equations. So here, of course, once we have isolated everything that has V on the left side and everything that doesn't have V on the right side, we can try to solve this. So we'll integrate both sides. So when we integrate on the left, we're going to have, this is 1 over V with respect to dV. This is going to be ln V. So the integral of 1 over V with respect to V will be ln V. On the right side, notice that 1 over CR, that's a constant. So the negative, the CR, these are all constant. I am basically integrating dt. The integral of dt will just be t. So basically the d and the integral will cancel, leaving me only with a t here. So this is what I now have. So at this point, of course, we know to say we didn't use any limits of integration, so you have to include a constant. The type of constant that we're going to use here, it can be anything really, but we're going to be strategic because we have a logarithm function here, a log function. We're going to say a type of constant we choose. We're going to strategically choose a log constant. It can be anything. Again, you can just put a C there, it's okay. But strategically, we're going to go with a log constant. So at this point, we want to get rid of this ln V. We just want V here. So when you, from there, when you take the antiln, which is the exponent on both sides, you're going to have E of ln V equal to E of -1 over RC, or CR, doesn't matter, plus ln A. E and ln will cancel. They are the opposite of each other. So that now on the left side, we only have V is equal to. On the right side, if you have A to the power X plus Y, this is the same as A to the power X multiplying A to the power Y. So I can look at the right side as E to the power -1 over RCT multiplying E to the power ln A. This is why we chose the constant to be a ln function, a ln expression, so that when you reach this stage, you can easily say the exponent and the ln will cancel. So now we have V is equals to that constant A, then E to the -1 over RC times T. This becomes the expression that tells us the response from the capacitor when it is as alone in a circuit with the resistor. This is the voltage response of a capacitor in a circuit when it is alone without any source. The type of response we are seeing here, because of the minus which is present here, this is an exponential decay. What does it mean in terms of what will happen to that circuit? It actually implies that if a capacitor is charged, you know to say when this is 0, when t is equals to 0 here, this part will be 0. When at t is equals to 0, this part will be 0. So if I plot a graph of the voltage response from a capacitor with respect to time, on the vertical axis I'll put voltage. What we see is that when t is equals to 0 here, we're going to have V is equals to A E to the power 1 over RC times 0. which will be 0. We see that when t is equals to 0, the voltage we will get, it will just be that constant we chose as A. What does this imply? It actually tells us that the voltage response from a capacitor is equal to the initial voltage when t is equals to 0 multiplying the exponent of minus t over RC. This is the expression we're going to get. So we can say at t is equals to 0, we start from here, where the voltage is basically the amount we have initially. But this starts to reduce with time until when the capacitor has been discharged completely. So this is an exponential decay, the curve we get here. So this is going to be an exponential decay. Okay. Now we can simplify this expression or write it in other words. It's okay the way it is, but we can define a new constant, and this is called the time constant. If we define the time constant and say this time constant is tau, we define this as, so we're going to define this as RC. If we define the time constant as RC, what happens here? In this case, notice that it now implies that in our expression, this becomes V is equals to the initial voltage stored multiplying the exponent of minus t over tau, where tau is that time constant. Okay, so any questions up to this point? If you're wondering what that time constant is, the time constant is just the amount of time. It is the time in seconds that is required for the response to decay to a factor of 1 over e, or it is the time required for the voltage here to reduce to 36.8% of the initial value. So the time it takes for this whole thing to reduce to 36.8% of the starting voltage, that time is what we are calling the time constant. So when you multiply R times the capacitance, what you get is going to be the time constant in seconds. So basically that is what we have there. You have to see here that with the expression for the voltage response from a capacitor in a circuit, we can use this voltage response to easily calculate, come up with the expression for power, for example. We can easily do that. And I have to say, in this case, notice that the circuit we analyzed to come up with that voltage response was a circuit where we did not have a voltage supply or a current supply, only that capacitor was in play. This type of response where the capacitor is just giving out what it has without any challenge from another external source being present, this is the natural response. So it actually refers, this voltage we are seeing here, it actually refers to the natural response of the circuit. Yeah, so this is what they'll refer as the natural response. As we go on, I think in our later classes, we'll look at the forced response as well. So we'll see the difference between the natural response and the forced response at that time. Okay, so let's consider this example where they're saying the switch in the circuit has been closed for a long time and it is opened at t is equals to 0. Find Vt for t greater than or equal to 0. So what does it mean? Let's understand this question first. Why are they saying it like this? What is the implication of each part here? The switch in the circuit has been closed for a long time. This statement tells us the initial state of what is happening here. Initially, when we get this problem, initially what was there was that the switch was closed. So initially we had this. This was, let me just do this. Okay, I want it to look different. Initially the switch was closed. We had that. So when the switch was closed, what was happening? So this is the circuit we had for t less than 0. For a long period of time, the circuit was like this. Now, what is the implication? It means that the capacitor was connected to a source, a voltage source. So what was happening? The capacitor was being charged. Because it was closed, it was connected to that source for a long period of time. It means that probably by the time the switch was being opened, the capacitor was fully charged. So the capacitor was fully charged. Now, when the capacitor is fully charged, what happens to it? When a capacitor is fully charged, it kind of stops the flow of current. So the minute the capacitor gets fully charged, it stops the flow of current. So here we're trying to understand how much voltage did the capacitor actually store. But to understand how much the capacitor stored initially, we first need to see what it does to the circuit when it's fully charged. When the capacitor is fully charged, it blocks current from passing through it. So it will block current from passing through it. And the best way to view it is to see it as if it is an open circuit, because no current will now be able to pass through that capacitor, or that line will be blocked out. So when fully charged, these terminals will now act as if they are open, they are not connected. The voltage stored in the capacitor initially, when it is still fully charged, will be equal to the open circuit voltage. So this is what comes out as the voltage stored in the capacitor initially for t equals to 0. So we need to find the voltage across these 2 points. That will tell us how much the capacitor had. Why are we looking for the voltage the capacitor had when the switch was still closed? Yet the problem is telling us to find the voltage it had when the switch was opened for t greater than or equals to 0. It's because in the formula for the voltage response from a capacitor, if you recall, the voltage response from a capacitor at any time t, this voltage response will be equal to the initial voltage the capacitor had just when the switch was being opened, multiplying negative t over the time constant. So to find the voltage response, we just need to know what the initial voltage was in the capacitor, and we also need to know what the time constant is. So in this case, we are first trying to find the initial voltage in the capacitor, which is the voltage the capacitor had when it was fully charged. So this is what we're trying to find here. This will be our V0. For a circuit like this, with the capacitor behaving the way it is behaving, notice that the voltage across the capacitor will now be the same as just the voltage across the 9 ohm resistor this side. because with the capacitor out of commission, not working there, the 1 ohm resistor there will act as if it is not part of the circuit. So our VC0 will just be the same as the voltage across the 9 ohm, because no current will get to pass through that 1 ohm, because where is it going? So we'll view our circuit as if it's just like this. 3 ohms here, 9 ohms here, and then the supply 20 volts this side. So that we just want the voltage across the 9 ohms. So since these two resistors, the 3 and the 9, they look like they are now just in series, so I can use voltage division. The voltage across the 9 ohm resistor, which will be the same as our V0, will be equal to the same 9 ohm resistor by voltage division divided by the sum of the two resistors in series, the 3 and the 9, multiplying the voltage they are sharing. So that now this is going to be 9 over 12 by 20. And if we do the math, this will give us 15. So this is our V0, the voltage the capacitor had when it was fully charged. Okay, what else? The capacitor was fully charged. The circuit was opened at T is equals to 0. What changed when the circuit was opened? Let's see. When the circuit was opened, now we have this opening here. What happens to our circuit? Notice that with the circuit or with the switch opened, now current from the source will have no route, meaning this entire line is not doing anything anymore. All in all, with the switch opened, the circuit reduces. The voltage source it becomes useless to the circuit. It's no longer doing anything. So the circuit can now be viewed without all this. Our circuit has reduced to just this. Fine. So now our circuit has reduced to just a source-free circuit, because now you see that there is no source here. So with the source-free, what is the total resistance in the circuit? The resistance here is 9. So the total resistance in the circuit here, you have to see that that is now just 10 ohms. So the time constant will now just be the 10 ohms multiplying the capacitance, which is 20 by 10 to the power minus 3. So this is now what becomes our time constant. With the time constant figured out, the voltage response from the capacitor will now be equal to V0, which is 15, e to the minus t over the time constant, 10 and 20, that is 30. So 30 by 10, 30, sorry, that is 200. So it will be 200 by 10 to the power minus 3. This becomes the expression that gives us the voltage response from the capacitor. So of course, this will be the same as just 15 e to the minus 0. That will be it will be t over 0.2. T over 0.2. This will be 0.2. So the 0.2 divides into 1, just becomes minus 5 t. So this will be the voltage response from that capacitor.